In this video we'll be talking about the natural response of an RL circuit, and to describe that we will be using this circuit. We assume that the current source generates a constant current of I of S, and that this switch has been closed for a long period of time. And by long period of time we mean that it has been closed for long enough such that all the currents in the circuit have achieved a constant value. In essence, this inductor has charged to maximum, and it is now acting as a short circuit. So all the current I of S doesn't pass through this resistor and this resistor anymore. They all now pass through the inductor. Then all of a sudden we open the circuit, we open the switch, and when we open the switch, this inductor and this resistor are isolated from the rest of the circuit, and this inductor begins to discharge the energy that has been stored in it through this resistor. Now the natural response of this circuit is the description of the voltages and currents across the terminal of this resistor as the inductor discharges. It is general convention to signify the time that the switch opens as time t equals 0, and the time prior to that, that is the time that it took the inductor to charge, to be time t less than 0. Then we take the time that it takes the inductor to discharge as time t greater than 0. So we proceed to draw out this portion of the circuit here, and by Kirchhoff's law we know that the sum of voltages in this loop is 0, and the voltage in the inductor is going to be L, the I, the T, and the voltage across the resistor is going to be IR, and their sum is going to be equals to 0. So as you can see, this gives us a first order differential equation, since we have the IDT here. The IDT is the maximum differential that we have here, and then we can rewrite this as L, the I, the T equals minus I R, which can be written as the I, the T is equals to minus I R over L. We can further simplify this as the I over I equals R the T over L minus R the T over L. If we choose to integrate both sides, which we definitely should, over I naught to I of T. So the I over I, and we integrate this over 0 to T minus R T over L. We arrive at ln I of T minus ln I naught equals R over L minus R over L into T minus 0, and this will give us in I of T over I naught equals minus R T over L. And ln is the same thing as log to base E of whatever is here. So we can write that as I of t over I naught equals e raised to power RT over L, which can be written as I of t equals I naught, that is the initial current, E raised to power RT over L. A more conventional way of writing this equation would be to write it as I of t equals I naught E raised to power minus RT over L. I naught is the initial current across the inductor before we switched we opened this switch. And with that, we can easily say that the voltage across the resistor, this resistor at any point in time, V, which is equals to IR, is then equals to V is equals to I naught multiplied by R E raised to power minus R T over L. With this much information, we can infer that the power I V is equals to I squared naught R E raised to power 2 RT over L. And this is going to be the expression for the power, and then further proceed to integrating this expression with respect to time. And if we do that, we'd have it that P integral upper limit lower limit t and 0 P dt, we would arrive at, I'm not going to bore you with the integration, I'm just going to show you, write it that we will arrive at half L I naught squared into 1 minus E to R over L T. And this is going to be the formula for the energy dissipated across the resistor at any point in time.